The work that we've done thus far on optics is really what we call geometric optics, looking at light going in straight lines and then bending as it slows down through different materials. But we haven't used the wave nature of light, that is, that it's made up of these oscillating electric and magnetic fields. And so we're going to look at some of the properties that come along with the wave nature of light. And so to do that, we need to think a little bit just about waves in general. And so one way we can think about this is, of course, a wave just goes up and down. And when we have two waves, we can add them together. We can have what's called superposition of waves. So if I have a wave traveling like this and another wave traveling in the same direction, then they can add together if they're crests and valleys. So that doesn't add up very well. But if they're actually lined up and they're traveling at the same speed, they can add together, and so you can get something that's really twice as big. So if you add them up, you can get something that's like twice the size, right? So this is called constructive interference. And you can have a situation sort of the other extreme is when you have these, again, these same waves where they have the same size, the same amplitude, and they're going the same speed, but in this case, they're traveling in such a way that they cancel each other out, so that when they run into each other, notice the peaks and the valleys are canceling each other out, and so you basically get this flat line. And sometimes this happens when you have waves traveling sort of in opposite directions and they cross through and they cancel out, and this is called destructive interference. And then, of course, you can have basically anything in between. These just have special names when waves are coming together or adding to each other. And so we're going to think about light and it being waves and trains of waves and having these waves add together. Now, in order to think about this, we need to have sort of a little bit of a different view about waves, not just that waves travel in straight lines, that light travels in straight lines, but this other idea that we know about waves even if we haven't realized it. And that is that waves, as opposed to thinking of light as just an arrow that goes through, waves actually can bend around corners, all right? And this is called diffraction. And you've seen it in water waves, right? If you have water waves, and I'm just going to draw sort of the peaks. So we have waves that are peaks here. I'll sort of highlight these peaks coming along. They hit this barrier, they hit an opening, and what happens is you can start to see, so I guess I'll make one more wave coming like this, and then the next peak comes through and it gets a little bent by the edges, because you can, one way you can think about it is sort of every point inside this wave is sort of the wave front for the next circular wave that's going out. You've actually seen circular waves going out, right, in when a rock gets dropped into a pool or something like that. And so what happens is when you have something that hits a barrier like this, you end up with these wave fronts getting bent a little bit. And so this gets bent just like if you had dropped a rock or something like that in the pool of water. We've sort of constricted the wave and it gets bent and it bends around. And so this bending of waves is called diffraction. It's light bending and spreading out. So where we might have light, I'll make it red light coming in like a red laser, hitting an opening, where you might expect, if we just treated light as going in straight lines, we might expect just a red dot right here. What happens is instead we get some red and it sort of fades out. It bends around the corner. Sound waves do this as well. This is why you can hear music around corners, is that it sometimes it reflects, but also it bends as it goes around corners. This allows you to hear the music from people down the hall from you. And so if we look at the intensity of this light, what happens is you get something that looks like it sort of goes up and goes down. So this is the brightest spot. This is bright, and then it goes down, but it turns out there's this point at which it kind of cancels. This is the destructive interference part. Destructive, where this light that came through this opening, right, comes through, that this light gets a little out of step at certain places. And so there's this place right here where light that maybe started here and light that started here end up, and they're just out of step. And so they are destructively interfering. Okay, and so this comes into play. This is sort of just the descriptive nature. We can actually derive where it is destructive and sort of the shape of this curve, but we're not going to do that for what we're doing in this class. What I want us to focus on is something called a diffraction grading, which is a whole bunch of slits that the light bends around and then can travel around as it goes. So we're going to focus on what it looks like when we have light that comes through a whole series of these slits, and we ask about where do they add together and where do they cancel each other out. Okay, and so that's what we're going to do. So here's our setup of a bunch of slits. You can see them over here. We'll zoom in on them in a little bit. And we're going to look at it. Turns out that you get definite bright spots. This is of constructive interference. It turns out with many, many slits, we get a bright spot. And we'll talk about why. So we get a bright spot here. We get a bright spot in the middle. This purple is the middle line. So this is a bright spot. Bright or constructive interference spot. And we can think about this being sort of the middle of the series of slits. So this one line is we can think of it as a light ray, like this, that comes and ends up over here. Okay, that's a train of waves coming. And then we look at what happens in the next door slit, okay? And if we line this up just right, oh, I haven't lined it up very well, then we can see, if we set up our waves just right, have the right wavelength, then I can get something where if this is the right wavelength, notice I've drawn it so that these are lined up together. And so what's happened is they're going to stay together for the rest of the time, if I've drawn this nicely, for the rest of the time until they reach this spot way over here where they're going to have constructive interference. And the difference between these two paths, so path 1 and path 2, is that on path 1, the light travels one extra wavelength, this extra distance right here. That distance is a wavelength. Okay? So path 1 has to travel one wavelength further, more than path 2. And then if we add path 3 right here, then that's going to be, path 1 will be 2 wavelengths more than this third one, and there'll be 1 wavelength difference between 2 and 3. And so if we keep everything 1 wavelength difference, 1 wavelength apart, like this is the first one, and it's coming up, and then the second one sort of comes up like this, you can see that they're all, I guess they start here, that they all match up with each other. They're all in step. So they all land at sort of the same place at the same time. And so they're all going to add together, and they're going to add constructively, because the only difference in their path is this 1 wavelength. So we're going to focus in on that. So here I've redrawn this same thing to show our path 1 and path 2, and we're going to focus on this little distance, right? So that little distance right there is one wavelength of the light, whatever the wavelength is, and that's determined by the color of the light. And so what I want to do is relate that to some of the parameters that we have that describe this setup. So this we're going to call a distance d, is the spacing between slits. So little d is spacing between the slits. And we can relate then when we have a bright spot here, this angle where we get a bright spot, we can look at our geometry and realize, hey, this is a 90-degree angle. This is theta, which means then that this angle right in here must be 90 minus theta, which means this angle right up there is also going to be theta. Okay, so again, just to repeat that, I have theta is this angle. That together with this angle right here, this red one that I'm coloring in right now, is 90 minus theta, which means that the angle that I'm highlighting right now, this one that I'm filling in, is again theta, just by our geometry here. Okay, once we have that as our angle, so I'm going to get rid of some of these things. Whoops. Then I can recognize if that's theta, then I can say that, in fact, sine of theta, this is kind of a weird triangle, right? This is 90 degrees there. So sine of theta is equal to lambda over d. And so that tells us what angle we're going to see this bright spot, right? This angle. And it actually doesn't have to be 1 lambda. It could be 2, right? This could be, right now I drew it as 1 wavelength, but it could also be 2 wavelengths or 3 wavelengths. So the general condition is that sine of theta, the location, this angle where we get a bright spot, is given by lambda over d, often times nd. Often it's written as d sine of theta is equal to n times lambda, where again d is our spacing between these, lambda is our wavelength of the light, right, our color, the color of light. And so we notice that this is going to depend on the color. As the wavelength gets longer, right, this d stays the same, then this angle must be smaller, and so we can actually separate this out by color, which is why with diffraction gratings it allows us to see the spectrum, the full spectrum of light. We can see the rainbow of colors. You can see your Roy G. Biv, if you like, coming through a diffraction grating. And this allows us to actually separate out the colors from different elements. If you've seen this in chemistry, different elements have signature spectra. So this is a good way for us to get at the spectra. We can measure then the spectra of stars, find out what they're made of, find out what atoms are in different things just by their spectral signature. So this is a really nice tool that we have to figure out what things are made of, and we can find that out just from the light that they give off. And it's all from using a diffraction grating. You'll see this, you may have noticed this with CDs back when you were kids. If you had a CD player, you might have noticed if you tilted it, you saw a rainbow of colors. That's because it's a whole series of these kind of bumps, really a grating of sorts. It's a mirror grating instead of a transmission grating, but it does the same kind of thing.